Hello all. In this video we will look at the Oracle complexity or the IFO complexity of SGD for strongly convex and smooth functions. Recall that we are considering the finite sum problem x star is equal to argmin over x capital F of x, where it is defined as 1 over n summation over I from 1 to n f of x comma xi I. The first assumption is that f is L smooth and mu strongly convex. We will use the stochastic gradient descent algorithm where we pick a random index it that corresponds to a random data point xi of it. Henceforth, we will denote this random point by xi superscript t. Then the update is of the form xt plus 1 equal to xt minus eta t into gradient of f xt comma xi of it. Also, we will use the notation et to denote the expectation with respect to xi of it or with respect to it. This way we can write et of gradient of f of xt comma xi of it is equal to gradient of f at xt. In this equation, both sides are random because xt is random. But on the left, there is an expectation with respect to it. When we are taking such an expectation, we must observe that the iterates xt depend only on I1 to it minus 1. Hence, xt is independent of it. Hence, we can evaluate the expectation with respect to it by averaging over all I from 1 to n. We can also take the full expectation on both sides. Expected value of gradient of f of xt comma xi of it is equal to expected value of gradient of capital F of xt. Now both sides of this equation are constants. Sometimes you may see another way of writing et, which is the expectation conditions on the past I1 to it minus 1. So that is just another way of saying the same thing. I must emphasize that we should pay attention to this particular process where we first take expectation with respect to it and then take it with respect to all other random variables. This is called nested expectation. And we will use this idea in the proof several times. In addition to the regularity assumption of each of the FIs, we also need a regularity assumption on how spread out the data is. Specifically, we will require that et of norm square of gradient of f of x comma xi t is less than equal to sigma square plus c times norm square of gradient capital F of x. Where recall that et is the expectation with respect to xi t or xi of it while keeping x constant. So this expression is imposing a restriction on the way in which the second moment of the stochastic gradient is growing. We can use this to calculate the variance of the stochastic gradient, which is bounded as Vt or variance with respect to it of gradient of f of x comma xi t is given by et of norm square of gradient of f x comma xi t minus norm square of et of gradient of f of x comma xi t, which is less than equal to sigma square plus c minus 1 times norm square of gradient of f of x. In case the stochastic gradient was simply a gradient, the variance would become 0. So sigma would be equal to 0 and c equal to 1 in that case. In the unconstrained case, where gradient of f of x star is equal to 0, this bound can be written as variance of gradient of f at x star comma xi of t is less than equal to sigma square, so which is essentially like bounding the variance of the objective at x star. You can verify that if you consider the least squares loss function and assume that the variance of the noise is sigma square, which is added, then all of these relationships would hold with equality. So this was our assumption on the variance of the stochastic gradients. Let us look at the Oracle complexity under these two assumptions, namely the strong convexity and smoothness of f and the variance bound on the stochastic gradients. The result is that if f is L smooth and mu strongly convex and has bounded second moment, then the number of IFO calls required to achieve that the expected optimality gap, which is expected value of capital F of xt minus f of x star, is less than equal to epsilon, is given by order of sigma square L divided by mu square epsilon. Observe here that the complexity is similar to what we obtained for the subgradient method under strong convexity assumption. In fact, the proof is also similar, except that expectations have to be handled carefully. Note that the complexity depends on the variance term sigma square, which is a property inherent to the dataset and how spread out it is. Interestingly, however, the complexity does not depend on capital N. So the complexity of stochastic gradient descent is the same regardless of the size of the dataset. Even infinite data is also allowed. That would be the case when data points are not from a dataset that is stored somewhere, but are instead generated from a process in a sequential fashion, like in a video, where frames are generated in a sequential fashion. So in that sense, stochastic gradient descent is much better than gradient descent when n is large, but it could be worse when n is small because the Oracle complexity in terms of epsilon is worse. Before beginning the proof, recall that at the tth iteration, we have xt that depends on the past random variables picked so far. That is I1 to I of t minus 1. Then we pick a random index it which is independent of xt. So that becomes the new random variable. If we take expectation with respect to it, it would be denoted by et. We could also use the full expectation with respect to all the random variables seen so far, which are the IID variables I1 to IT, and that is denoted simply by E. This gives rise to xt plus 1, which would now be a function of the random variables I1 to IT. So let us look at the proof. The first step is to use the smoothness and the properties of the stochastic gradient. We begin with using the quadratic upper bound on capital F, which yields that capital F of xt plus 1 is less than equal to capital F of xt plus inner product of gradient f of xt, xt plus 1 minus xt plus L by 2 norm square of xt plus 1 minus xt, which can be written as f of xt minus eta t times inner product of gradient f of xt, gradient f of xt, xi t plus eta t square L by 2 norm square of gradient f of xt, xi t. So here we have just used the update equation. Recall that xi t is the shorthand notation for xi of it. Now let us take expectation with respect to it and use the fact that it is independent of xt. So et of f of xt plus 1 is less than equal to f of xt minus eta t times inner product of gradient f of xt, et of gradient f of xt, xi t plus eta t square L by 2 et of norm square of gradient f of xt, xi t. Here we have been able to take the expectation inside the inner product because taking the expectation with respect to it, the term gradient f of xt is simply a constant. Now we had assumed that the stochastic gradient is unbiased, implying that the expectation with respect to xi t of gradient f of xt, xi t is equal to gradient capital F of xt, which means that the last term is equal to f of xt minus eta t times norm square of gradient f of xt plus eta t square L by 2 into expectation with respect to xi t of norm square of gradient f of xt, xi t. Now the last term can be bounded using the bounded moment assumption, which yields that et of f of xt plus 1 less than equal to f of xt minus eta t times 1 minus eta t LC by 2, norm square of gradient f of xt plus eta t square sigma square L by 2. Let us assume that eta t is less than equal to 1 over LC, so that the term 1 minus eta t LC by 2 can be replaced by half. And we get that et of f of xt plus 1 is less than equal to f of xt minus eta t by 2 norm square of gradient f of xt plus eta t square sigma square L by 2. Next, recall the PL inequality, which is the implication of the strong convexity of capital F, but may also be true otherwise, which says that half of norm square of gradient f of x is greater than equal to mu times f of x minus f of x star. So using this bound on the second term and subtracting f of x star on both sides, you can see that we get expected value of f of xt plus 1 minus f of x star less than equal to 1 minus mu times eta t times f of xt minus f of x star plus eta t square sigma square L by 2. This is not yet the one-step inequality because we have expectation with respect to it on the right, but there is no expectation term on the left. To remedy that, we take full expectation with respect to I1 to it on both sides, so as to get expected value of f of xt plus 1 minus f of x star is less than equal to 1 minus mu eta t times expected value of f of xt minus f of x star plus eta t square sigma square L by 2. If you recall, this form of recursion is exactly the same as we encountered in Frank-Wolf and subgradient descent algorithms. If we denote the expected optimality gap by delta t equal to expected value of f of xt minus f of x star, then this can be written as delta t plus 1 is less than equal to 1 minus mu eta t times delta t plus eta t square sigma square L by 2. Let us substitute the step size as 2 over mu times t plus 1, assuming that this quantity is less than equal to 1 over LC. Then we get delta t plus 1 less than equal to t minus 1 by t plus 1 into delta t plus 2 sigma square L divided by mu square times t plus 1 square. Next, as in the case of subgradient descent, we multiply both sides by t into t plus 1, so as to get t into t plus 1 into delta t plus 1 less than equal to t into t minus 1 delta t plus 2 sigma square L by mu square t by t plus 1. Here we will simply bound the term t by t plus 1 by 1. Then it is possible to carry out the telescopic sum, which yields that t into t plus 1 into delta t plus 1 is less than equal to 2 sigma square LT by mu square, or delta t less than equal to 2 sigma square L by mu square t. So equating this to epsilon, we get the required IFO complexity bound. The result will be slightly different if we don't have to assume that eta t is less than equal to 1 by LC. As we mentioned earlier, the remarkable thing about this performance bound is that there is no dependence on n. In case the assumption about 1 by mu being less than equal to 1 by LC is not true, that is, when mu is less than equal to LC, a slight modification gives us the same bound. In that case, we can take eta t equal to 2 divided by mu times t plus k, where k is equal to floor of 2 LC by mu, which is greater than equal to 2 because we assume that mu is less than equal to LC. So this way we can ensure that eta 1 is given by 2 divided by mu times k plus 1 is less than equal to 1 by LC. The analysis for this case is almost similar. The recursion becomes delta t plus 1 less than equal to t plus k minus 2 by t plus k into delta t plus 2 sigma square L divided by mu square t plus k square. So we can again multiply both sides by t plus k into t plus k minus 1. So that gives us t plus k into t plus k minus 1 delta t plus 1 less than equal to t plus k minus 2 into t plus k minus 1 delta t plus 2 sigma square L by mu square into t plus k minus 1 divided by t plus k. So here we can bound the t plus k minus 1 divided by t plus k in the last term by 1, and then taking the telescopic sum we obtain capital T plus k minus 2 times t plus k minus 1 into delta t is less than equal to k into k minus 1 into delta 1 plus 2 sigma square L by mu square into t minus 1. So this translates to delta t less than equal to order of sigma square L by mu square t plus L square c square bf by mu square t square. So here if we ignore the higher order 1 by t square term, the performance bound is same, and therefore the IFO complexity is also the same. We have already seen the example of neural networks where the objective function is non-convex. For non-convex but smooth f, the result is that the number of IFO calls to ensure that the minimum over t expected value of norm of gradient of f of xt is less than equal to epsilon is given by order of sigma square L bf by epsilon raised to the power 4. Observe again here that while this is much worse than what we had in gradient descent in terms of epsilon, it does not depend on capital N and can be used for arbitrarily large data sets. The proof for this non-convex case utilizes the exact same first step as in the convex case. So we can refer back to that proof and write down the inequality that we had obtained, which is that expected value of f of xt plus 1 less than equal to expected value of f of xt minus eta t by 2 expected value of norm square of gradient f of xt plus eta t square sigma square L by 2, provided that eta t is less than equal to 1 by LC. Now instead of applying the PL inequality, in this case we can simply carry out the telescopic sum so as to obtain that expected value of f of xt plus 1 is less than equal to f of x1 minus half summation of t equal to 1 to capital T eta t of expected value of norm square of gradient f of xt plus eta t square sigma square L by 2. Since f of x star is less than equal to f of xt plus 1, we can rearrange and write this inequality as summation over t equal to 1 to capital T eta t of expected value of norm square of gradient f of xt less than equal to 2 times f of x1 minus f of x star plus summation over t equal to 1 to capital T eta t square sigma square L, which is less than equal to 2 times bf plus summation over t equal to 1 to capital T eta t square sigma square L. So this can be written as minimize over t expected value of norm square of gradient f of xt less than equal to 2bf plus summation over t equal to 1 to capital T eta t square sigma square L whole divided by summation over t eta t. Now finally we use the fact that expected value of x is less than equal to square root of expected value of x square, which yields that minimize over t expected value of norm of gradient f of xt is less than equal to square root of 2bf plus summation over t equal to 1 to capital T eta t square sigma square L whole divided by summation over t eta t, which is the key performance bound. It remains to choose the step size appropriately. First we consider the case when eta t is equal to eta for some eta, then we get that minimum over t expected value of norm of gradient of f of xt is less than equal to square root of eta sigma square L plus 2bf by eta t. So if we equate this to epsilon, we will obtain that eta is equal to epsilon square by 2 sigma square L and t is equal to 4bf by eta epsilon square, which is equal to 8 sigma square LBF by epsilon raised to the power 4. So this is the required Oracle complexity bound. We can get a similar result for the diminishing step size case. Adaptive step sizes are also possible, but the analysis gets much more complicated in case of SGD because of the expectation operator that needs to be carefully applied in the proof. So that is all for this video. We have seen the Oracle complexity of SGD for both convex and non-convex cases. We have seen that as compared to gradient descent, there is no dependence on n, and hence SGD is applicable to arbitrarily large data sets or to streaming data as well. In the next video, we will see the momentum enhancement possible for SGD.